Now that we talked about the details of the central limit theorem and what it says, let's go through an example. You should have your calculator handy. I will tell you what buttons to press. I don't have a nice screen to show you like I normally do in class, so do your best to follow along. Now, if you're reading my notes, it says an unknown distribution. Okay, that's important here. We don't know whether it's a normal distribution, whether it's a binomial distribution, uniform, exponential, none of that, okay? So it'd be a great time to use the central limit theorem here. It says the unknown distribution has a mean of 90. It says it has a standard deviation of 15. And then it says samples of size n is equal to 36 are drawn randomly from the population. Now let's read that one more time. It says samples. There's plural there, okay? Meaning we're drawing more than one sample, okay? Here's what we're doing. Here's our population. Here's one sample, sample 1. It has some mean x bar 1. We draw another sample, S2. It has some mean, x bar 2. We can do it again, S3, x bar 3. We keep doing it over and over. They all have the same sample size, 36, okay? Now let's read the question. Find the probability that a randomly selected sample mean is between 85 and 92. Okay? Find the probability that a randomly selected sample, so we're randomly selecting a sample from the list of all of our samples of size 36. What is the probability that our average of that sample is between 85 and 92? This should sound a lot like the Chapter 6 problems, because we're going to solve it just like the Chapter 6 problem, okay? We're going to use normal CDF. So let me draw you a picture. We have mu of x bar, our sample mean, mean of our sampling distribution, according to the central limit theorem, that is equal to exactly our population mean. I usually draw this dotted. There we go. Now we want to know what is the probability that we are between 85, so 85 and 92. We want that area right there. To find that area, normal CDF, well, they told us our lower bound was 85. They told us our upper bound was 92, comma, I'm running out of space, so I'm going to put it down right here. The mean stays the same, comma. Well, now since we're using the central limit theorem, the standard deviation for our sampling distribution is equal to sigma divided by square root of n. So I'm going to put 15 divided by square root of 36 right there. Okay? And this is what I'm going to enter in on the calculator. It's, like I said, very much like Chapter 6. The only thing is you got to change your standard deviation right here. You got to divide it by the square root of your sample size. So let's see, I put 85, 92. So I go second, and then I go to vars. That's to get to my distribution. I went to normal CDF, and now I'm just typing in my my inputs here. 15 divided by square root of 36. When you do it on the calculator here, I could do this. Let's see. If you look at how I typed in my standard deviation, I didn't calculate first 15 divided by square root of 36. I typed it directly in on the calculator as you see it, and then as soon as you hit, I thought if you hit down it would change it, but it will calculate that number for you. You do not have to figure out what it is beforehand. Just type it in exactly like that, and now you can hit enter, and enter again, and you get a probability of 0.7653. So you have about a 76.5% chance that if you pick a random sample from your sampling distribution, it should have a mean between 85 and 92. Okay. Now, part B. Find the value that is 2 standard deviations above the expected value of the sample mean. So all that's asking you to do, so let me draw you a picture. See, here's mu x bar. We go out one standard deviation of x bar. We go out another standard deviation of x bar. So find the value that is 2 standard deviations above the expected value for the sample mean. So that's just saying take our sample mean, not equals, and add 2 sampling standard deviations onto it. So this was 90 plus 2 times 15 divided by the square root of 36. And then this just becomes a simple calculator entry. 90 plus 2 times 15 divided by square root of 36. And you get 95. So 95 would represent 2 standard deviations above the mean. Okay? Now, I've got another example we're going to go through. It's going to be very similar. Just change the scenario. Let's see. It says, in a recent study reported October 29, 2012 on the Flurry blog, the mean age of tablet users is 34. So the average age of tablet users is 34 years. Suppose that the standard deviation is 15 years. Take a sample of size 100, so n is equal to 100. What are the mean and standard deviation for the sample mean age of the tablet users? So that part A is telling you to find mu of x bar and find sigma of x bar. Well, mu of x bar is just equal to whatever the population average is. So this is 34. And then sigma x bar is whatever the standard deviation is divided by the square root of the sample size. So this is going to be 15 divided by square root of 100, or 15 over 10, or 3 halves. 1.5 if you want a decimal. Really doesn't matter. It's a nice decimal. Okay, so now let's see. What does the distribution look like? Well, since we're using the normal distribution, or since we're approximating things using the normal distribution because of the central limit theorem, we could say that our random variable x is approximately normal with the sampling average of 34 and a sampling distribution of 1.5. And this is what the distribution would look like. I know when they ask what it looks like, you might think of what it looks like, draw a picture. Well, this tells you how the picture should be drawn. It should be drawn normal, centered at 34, because that's where the average is, and then the standard deviations are 1.5 away. Okay? Now it asks us questions to find probability. We don't need this information here. We could actually just have this piece here. I'll write it over here. X is approximately normal, 34, 1.5. So that tells us our information that we need to compute the next part C. Find the probability that the sample mean age is more than 30 years old. Okay, if I were to draw this on a picture, 34 would be in the middle. And then we want to know what is the probability that someone is 30 years old. finding the sample average is greater than 30 years old. So greater than would be everything this way. And again, we're going to use normal CDF. Normal CDF. Well, my lower bound's 30. My upper bound, this keeps going on forever. You need to make it a large number. I'm going to use 100. 34 here. Now, we already calculated what sigma divided by the square root of n is. In the previous problem, we didn't calculate it beforehand, so that's what we put right here. But since we already calculated what this value was beforehand, we're just going to put a 1.5 right there. Now, you could instead do the 15 divided by square root of 100 right there. That would be the same thing. These two are equivalent. It doesn't matter, okay? Point is, you do not have to take this number and divide it by the square root of 100 again. We already did it once. Okay, so now all we have to do is punch this in on the calculator, and we're done here. So 30 lower bound, 100 upper bound, comma 34 average, comma 1.5 standard deviation. Hit enter. Ooh, this is a really high probability. 9961. 0.9961. So, what this is saying is that if we keep taking samples of size 100, 99% of the time, if we were to pick one at random, we should expect the average age of that sample to be greater than 30.